So let's say we want to build a histogram for these 7 numbers. The first thing we should do is create a set of axes, and along the x-axis we're going to be creating bins. So basically we'll just be binning up these numbers, and on the y-axis we'll be counting up how many numbers we've seen in each bin. Let's try it out. So our first number is 6. If we'd like to place that in the appropriate bin, it would go right here, between 5 and 7. So that means we've seen 1 value in this bin so far, and our count on the y-axis shows that we have 1 value within this bin. Let's try the next number. Number 1 we'll put in this bin, so each bin includes its lower bound. And once again, the count for that bin now is at 1. We can move on to the number 3, which goes right here. And next we're going to come up on the number 5, which goes in that bin between 5 and 7. So what's going to happen now is we'll actually increase our counter to show that we've now seen 2 values within this bin. And here's another 5. It goes right there. So this counter is now at 3. Our final couple numbers, 8 goes over here and 4 goes over here. And so there we go. At this point, we have created a histogram for these values. But most of the time when you're creating histograms, you're going to have way more than 7 values. And the benefit of having a lot of data like this, we can start to get a sense of what the underlying distribution looks like for these data. In fact, this can even help us estimate the probability density function. So maybe you have some data that looks like this, and you want to get a sense for what the underlying distribution looks like for these data. You probably already know you could create bins and count up the number of values within each bin to create a histogram. But you can also create a smoothed out continuous version of this histogram with something called KDE, or kernel density estimation. The KDE plot, it's really quite simple. We're going to start with a set of finite data. Here I just have 6 data points, but of course you could have more. Then we're going to add in a little kernel centered about each data point for every single data point. And eventually all I need to do is just add these together. So as I'm adding each of these together, you'll see that I'm getting closer and closer to a probability density function, and the end result is going to be our kernel density estimation. So the box plot actually contains several different component pieces, so I want to walk you through each piece individually. The first thing I do when I draw a box plot is find the median. So let's say I have data like these. All I'm trying to do is subdivide this data so that 50% of it lives on the left and 50% of it lives on the right. Once I've found this value, I'll draw a line representing the median. Now I'm actually going to focus down on just the lower half of this data. Once again, I want to subdivide this data so that I have 50% on one side and 50% on the other. But remember, I'm already working with half of the data. So half of half is now 25% of the data. And once I've found this 25th percentile, I'm going to draw another vertical line. Focusing over on the upper half of data, I'm just going to do the same thing again. Subdivide this data and then draw a line. And there you have it. Each of these lines represents the 25th percentile, the median, and the 75th percentile of your data. Once you have these 3 lines, all that's left to do to construct the box portion is just to connect the lines. And we usually fill this in with a color. That's it, that's the box part. The other part of this graph represents something called the whiskers. So to build the whiskers, I actually start by measuring the inner quartile range. So this is the distance from the 25th percentile up to the 75th percentile. Once I know that distance, I'm going to stretch the whiskers out in either direction, 1.5 times this inner quartile range. But it gets a little bit trickier than that. So let's go ahead and focus on the left-hand side first. This is, I think, the trickiest part of building a box plot. So I want to go ahead and build this left-hand whisker. Instead of strictly following this guideline, however, I actually only stretch out the whisker until the last data point that lives within the 1.5 times inner quartile range. For us, that's going to be a much shorter whisker, and I'm only going to go down to the value at 1. When I try to build the whisker on the right, I stretch out the whisker and see that there's actually one data point that falls outside of my 1.5 times interquartile range, this one right here at 12. So instead of extending that whisker out, I actually shrink it back to, again, the last value that lives within this range, or the value at 8. The final data point, because it lived outside of that 1.5 times interquartile range, actually I'm going to label that as an outlier and put a little diamond shape here. And that's it. That's how you build a box plot. So each component piece of the box plot tells you something different about your data. And the other nice thing is that you'll often be able to split up your data into different categories so that you actually have two different boxes that you can compare the distribution between your various categories. There's a pretty clear recipe for building a violin plot. Take 1 part box plot and not 1, but 2 parts KDE plot. Mix those two together and your violin plot is formed. Violin and box plots share several of the same key landmarks. For example, you can find the median of your data, as well as your data's interquartile range. And remember, that just ranges from the 25th to 75th percentiles of your data. You can also get a sense of your data's extended distribution via these whiskers. But there are a couple of key differences. The box plot alerts you to potential outliers in your data, whereas the violin plot features a kernel density estimation for your data's probability density function. Let's say that you own a cafe and you track the average number of each beverage you sell on each workday. With tabular data like these, it can be really difficult to notice that coffee is your best seller on Wednesdays, or that soda is your worst seller. In a heat map, you're just going to map each value to a particular color so that you can find these insights much quicker and so that you can communicate your results to others. To build a strip plot for these data, I'll first start with a blank number line. Then I want to create a scatter point for each value in my data set. So here's the value at 4 and at 5, etc. But something happens when I get to the second number, 1. If I try to create yet another scatter point in the same position, you'll see that I can't see the new scatter point, so I have a collision. And the same thing happens when I get to the number 4. And by the time I finish filling out the full 8 data points, I can actually only see 6 scatter points. So the strip plot gets around this issue with something called jitter. That basically just means I'm randomly going to move each dot either a little above or below this line so that I can see all 8 data points. And now we have our strip plot. To build a swarm plot, you can think about sorting your data and then grouping it up by value. Now we just want to add 1 circular dot for each data point. So for example, I have 5 1s and I'll just put 5 circles in the 1 position. I have 2 2s and 1 3 and so on. Until eventually I have 1 circular dot for every single data point. You can also see that none of those circular dots overlap, and that is a property of the swarm plot.